So today I'm going to talk about a generalized Aviles-Giga functional. And this is from with Lamy, who just gave a talk earlier this morning, and Lorent at the University of Cincinnati in the US. So here's what I plan to discuss. I'm going to start with a brief overview of the classical Aviles-Giga functional, and then I will explain the generalized energy functional that we did today. And then in the last part of the talk, I will try to explain our main results and hopefully also some new ingredients in the work. Okay, so the classical Aviles-Giga energy functional is the second order energy functional. So here I call it A sub C. I use the subscript C to just indicate that this is the classical energy to distinguish it from the generalized energy that I'm gonna discuss later in this talk. So this is defined for a scalar valued function U, and it's a second order energy. So the first term is the Hessian matrix of the function U, and there is a small parameter epsilon in this energy. In the second term, the potential term, that takes the form of 1 minus the norm of grad U squared divided by this small parameter epsilon. So, well, by the way, in this talk, I will just talk about this problem and the related problems in 2D only. In higher dimensions, not much analysis has been done so far. So this energy has applications in various settings, including smectic crystal, thin film blisters, and convection pattern formation. So we can do a quick comparison between this energy and the well-known first-order multiple Mortola. So this is the first-order multiple Mortola with a gradient term and a double well potential. And here I'm stating the gamma convergence in 2D. So it's well known that if gamma converges to C times this limiting energy that catches the jump. So here, this is the jump set of the function U, and these are the traces of the function U across the jump set. So these are well defined for BB functions. So this gamma convergence occurs over the BB space. Then for the by the way, so if you replace the scalar valued function U by its gradient in the multiple Mortola, then essentially that is the Aviles-Giga energy. So for the Aviles-Giga energy, the conjectured gamma limit takes a similar form as this one, except that we have a jump to the power 3. So this is what already appeared in Xavier's talk. So here, this is the jump set of gradient of U, and these are the traces of grad U on the two sides of the jump, assuming these things are well defined. So basically, this jump makes the following has been natural. So what is the function space for the gamma convergence? Because we don't expect this limiting energy to be defined over the BB space. And in fact, there is an example constructed by Ambrosio, Delalis, and Mandigazza. So they constructed a function U so that this energy is finite, but grad U does not belong to BB. So here, one of the central questions is the structure of the function space. And then for the gamma convergence of this problem, so the lower bound part, I mean the limit inequality and compactness are settled. Specifically, the compactness was proved by these two groups of authors independently. So collecting their results, essentially they showed that if you have a sequence U epsilon with equivalent energy satisfying this soup of the energies being finite, then there is precompactness in the gradient. So up to a subsequence, grad U sub epsilon converges to grad U for some limiting function in the L2 space. And further, this limiting function satisfies this Eikonal equation, basically just because of the second term in the energy. And the proofs of both groups of authors basically used this important tool of entropies. The first group of authors, Ambrosio, Delalis, Mandigazza, they used a special class of entropies that was first introduced by Jin and Kohn. And then, so the second group of authors, this Moni, Muller, Kohn, and Otto, they really made this notion of entropies in this setting more explicit and more systematic. So following the presentations in the work of this Moni, Muller, Kohn, and Otto, so we can reformulate this Eikonal equation in 2D as a scalar conservation law, as we mentioned in his talk. So we introduced this auxiliary vector field M, which is grad perp of U. So that's a rotation of grad U by pi over 2. And then, so this vector field M, first is a unit vector field, and then it's a rotation of a gradient. So it's a divergence free in 2D. So I mark this equation by E. It stands for the Eikonal equation. And then we can write out the divergence free equation. So partial 1 M1 plus partial 2 M2 equals 0. So then using the fact that this M is a unit vector field, we can write this M2 as this function of M1. So here I put a negative sign in front of that just to make the function convex in M1. And then plugging this into the first equation. So this can be realized as a scalar conservation law for M1 if we think of this first the spatial variable as the time variable with this nonlinear flux function. And then, so this group of authors formally defined the entropies for the Eikonal equation in 2D. So in this setting, entropies satisfy the following two important properties. So the first important property is similar to what entropies would do for scalar conservation laws. Namely, if you take a sufficiently regular solution of the Eikonal equation, say smooth solution, then the divergence of entropies applied to M are 0. So these are called entropy productions. And further, so there is the following important estimate that connects entropy productions and the Aviles-Giga energy. So if you take, well, by the way, here I'm formulating the Aviles-Giga energy in terms of this auxiliary vector field M, that's a rotation of the gradient. So if you formulate the energy in terms of M epsilon, which is a gradient already, then the energy is a Ginsburg-Landau type energy with a divergence-free constraint. So if we take a sufficiently regular admissible vector field M epsilon for the Aviles-Giga energy, then direct calculations show that we have the following estimate. If you take the integral of the entropy production against any test function, so this can be controlled above by some constant depending on the entropy phi, multiplied by the Aviles-Giga energy of this vector field M epsilon, multiplied by the sup norm of the test function. And then there is a lower order term that is on the order of a certain power of epsilon. So the significance of this estimate is twofold. First, this offers a lower bound for the Aviles-Giga energy. So then together with the compactness result, one can show the Lamy inequality in the gamma convergence in terms of entropy productions. On the other hand, this also offers a upper bound for entropy productions, again, together with the compactness result on the previous slide. So this gives us something about entropy productions in the limit. So if you take a sequence with equibounded energy, then according to the compactness result, there is a precompactness in the L2 space. Then if you pass to the limit in this estimate as epsilon goes to 0, so the limiting function will be something that satisfies all entropy productions are finite real measures. And this suggests the space for the gamma convergence of the Aviles-Giga functional, that is the finite entropy solution space for the Eikonal equation. By the way, here what I call finite entropy solutions correspond to what Xavier called the entropy solutions. So the entropy productions are finite real measures. And this notion of solutions has also received significant attention for scalar conservation laws. In general, these solutions don't enjoy, I mean, they have a weaker regularity and they're not in the BB space, but nevertheless, they enjoy BB type properties, as Xavier mentioned. So the next slide, I'm just listing this result of Tilelis and Otto. So Xavier already explained this very well, so I just go through this rather quickly. Essentially, they showed that for a finite entropy solution of the Eikonal equation, there exists this 1D jump set, and one can define traces on the jump set, and entropy productions can be calculated explicitly using a formula that is similar to the BB chain rule, and then away from the jump set. So we have a vanishing mean oscillation points of M. And then they conjectured that the first and the third points can be improved to first the Lebesgue point for the first point. This is as Xavier talked about in his earlier talk. So they made this a significant progress towards this conjecture. And further, although the entropy reductions can be computed explicitly on the jump set, away from the jump set, the structure is still not very well understood. So the conjecture is indeed entropy reductions are concentrated on the 1D jump set. And so along this line, there's these recent significant progress by Marconi, who proved similar conjectures for Berger's equation and also a related micromagnetics model that was first studied by Xavier and Serpati. Okay, so on the next slide is just a sort of a summary of the relevant literature. Well, this is not meant to be exhaustive on this Aviles-Giga functional. So first, for the gamma convergence, many authors have made significant contributions to this important problem in the calculus of variations. In particular, I mentioned the compactness result by these two groups of authors. And also the Lamy inequality was also proved by Ambrosio Villalis-Montegaza using a special class of entropies. And under an additional assumption that either gradient of U or M belongs to the PV space, the Lim-Sup inequality part of the gamma convergence was also settled by Conti-Dilatis and Poliakowski independently. However, without the additional BV assumption, the Lim-Sup part still remains open. And the full proof of the gamma convergence would require better understanding of the structure of finite solutions of the Eikonal equation. So along this line, there is also many significant progress towards understanding this important function space. And also there is interest on related problems, for example, kinetic formulation for finite entropy solutions, regularity of zero energy states, and also the scope of entropies for more general line energies. So this is just a quick overview of the classical Aviles-Giga functional, and then let me try to point out the generalized energy functional that we recently studied with Xavier and Andrew. So this is the generalized energy that we looked at recently. So here again, I'm formulating the energy in terms of this rotated vector field M. So M is a grad curve of U. And then the energy becomes a first order energy of the Ginzburg-Landau type. But because M is the rotation of a gradient, it must be divergence free. So there is a divergence free constraint in this energy. So here I use the subscript G to indicate that this is a generalized energy functional. And then compared with the classical energy functional, here we're replacing the Euclidean norm of this vector field in the potential term by a more general norm. So here we assume this more general norm to be strictly convex C1. Well, by that we mean if we denote by capital B, the unit ball of this norm, then this is a strictly convex body. And then if we denote by capital gamma, the unit circle of this norm, then this is the C1 curve. So this problem was first studied by Bochard and Pegon. I'm not sure if I pronounced their names correctly. So they studied this problem with a focus on understanding regularity of the zero energy states. So I will come back to explain zero energy states in just a moment. And then more recently, there is another work by Eikonal and Montel. So they also studied similar generalized Aviles-Giga functionals, but the focus is to understand the symmetry properties of entire critical points. And then in our work with Xavier and Andrew, so we looked at took a closer look at this energy functional, and our goals are twofold. So we wanted to understand what parts of the classical Aviles-Giga theory are contingent on the Euclidean norm and what parts are more flexible. And also we wanted to better understand the finite entropy solutions for scalar conservation laws. Okay, so here, heuristically speaking, because of the potential term in this energy, in the limit, we expect the limiting function to satisfy what we call a generalized Eikonal equation. So that is this general norm of M equals 1 almost everywhere, and M is divergence free. And then I mark this equation by GE, so that stands for generalized Eikonal equation. And then as a first step in our analysis, we had to identify the appropriate class of entropies for this generalized Eikonal equation. Just similar to the classical setting, we require entropies to satisfy two important properties. The first one is the natural one. So if you have a solution of the generalized Eikonal equation, then entropy productions should vanish. So here, just similar to the classical setting, so we require entropies to be something defined on gamma, where this gamma is the unit circle of the norm. That is where this vector field M lives in this setting. And then they take values into R2. So here, this gamma is just a C1 curve in general. So the best general regularity we can assume on phi is just a C1 mapping. So then in order to make this condition more explicit, we can introduce a arc length parameterization of the unit circle of this norm. So here we're assuming implicitly that the length of this curve capital gamma is 2 pi. Well, it's not using generality because otherwise we can always do a rescaling. So after having this arc length parameterization, then direct calculations can translate this condition into the following equation. Namely, the derivative of this phi applied to gamma theta, so it has to be tangent to gamma at every point. In other words, it's a scalar multiple of the unit tangent on the curve gamma. So this is for all theta. And then further entropies have to satisfy the important estimate connecting entropy productions and the energy. So this is what happens to entropies for the classical Aviles-Giga functional and Eikonal equation. So here we require such a type of estimate. Well, then through some careful calculations, we realized that for merely C1 entropies, generally this estimate does not hold. So we need to require a little bit more regularity for entropies. It turns out that in order for this important estimate to hold, we require this function here to be further a C1 function. So the entropies are C1 mappings, but they have to enjoy a little bit more regularity in order for this estimate to hold this.
So how do you extend phi from your gamma to because MF sign?
Yes, so that's a good point. So here we're taking something that is admissible for the energy. So in general, it's not living on the unit circle of this norm, then we can do a sort of a radial extension. But here, in fact, what we did was that we chose a transformation to transform the unit circle of this general norm to S1, and then we did calculations for, and then after the transformation, the vector field becomes something that is S1 valued, but satisfies a more general divergence-free condition, and then we did entropies for that in that setting.
So morally, phi is extended on the normal to the gamma, like radial in the normals to the gamma.
So, yeah, morally speaking, like that way. But since we did this transformation, then in the S1 setting, it's a really radial extension. But when you translate back, then it's shifted by this transformation.
Right.
Yeah, but morally speaking, you're right. So it's kind of a radial extension, morally speaking.
Like, does it depend on how people do? Because you can imagine there's lots of.
Actually, in some of our works, we chose different types of extensions, and then we got different. And when talking to the limit, we got different information. Sometimes we have to make careful choices of the extensions in order to get what we want. But here, the focus is rather to, here we mostly just focused on what's happening really on this unit circle of this norm. So if we choose different types of extensions, then after passing to the limit, so whatever extension we choose on the circle, it has to agree with the entropy. So after passing to the limit, it gives the same information. But in other cases, we did choose different types of extensions and then leading to different kind of information. Okay, so here then, with the help of, well, this is the class of entropies for this generalized Eikonal equation and the generalized Aviles-Giga functional with this important property satisfied. So if you have the entropy production tested against a test function, so there is this bound by the energy times the supernorm of the test function, and there is error term. So this is similar to what happens for the classical Aviles-Giga energy and the classical Eikonal equation. Okay, so now with the help of this appropriate class of entropies and this important connection between entropy productions and the generalized Aviles-Giga energy, first, we're able to show the following compactness result. So this is essentially similar to what Ambrosio, De Lellis, Mantegazza, and Dismoni, Muller, Kohn, and Otto proved for the classical Aviles-Giga functional. So we take a two-dimensional bounded open set, and here we take a strictly convex C1 norm, and suppose we have a admissible sequence for the generalized Aviles-Giga functional, namely sufficient regularity, divergence free, and also satisfying this equiboundedness of the energy. Then we show that there is compactness in M epsilon in the L2 space. Again, this is very similar to the work by these two groups of authors on the classical Aviles-Giga energy. So here the proof just follows rather closely the roadmap used by this second group of authors. So specifically, they used this compensated compactness argument with the help of all entropies to show all Young measures are Dirac measures. So we followed pretty closely this roadmap, but with some technical adaptations to this our generalized setting. So I guess it's no need to explain that further. So here I just want to mention briefly that the strict convexity of this norm is necessary, because otherwise, if the unit circle of this norm has a flat piece, then one can easily construct a sequence of functions taking values on this flat piece, but with higher and higher frequencies of oscillation. So there is only weak compactness, weak convergence in that case. Okay, so then next, let me try to.
Sorry.
So next, let me discuss a little bit about the so-called zero energy states. Here, I'm kind of combining the definitions for both the classical case and our generalized case into a single definition. So a zero energy state is a solution of the Eikonal equation or generalized Eikonal equation, so that all entropy productions are zero. So here the entropies are those for the classical equation or our generalized equation. And well, in fact, these zero energy states come from limits of sequences with energy converging to zero. So that's how they got their names. And then for the classical equation, the first systematic study of zero energy states was carried out by Xavier, Otto, and Pegon. So they showed that zero energy states of the classical Eikonal equation can have only vortex singularities, and away from the vortex singularities, the vector field M must be locally Lipschitz continuous. And in the work of Bochard and Pegon, they studied the generalized energy functional that I mentioned a couple of slides ago, and they basically extended this regularity result to this generalized setting. Specifically, they showed that if M is a zero energy state of the generalized Eikonal equation associated with a C1 norm of power type P, well, here this power type P condition, non-technically speaking, this is a quantitative form of a strict convexity. So it's a little bit more than strict convexity. And then they showed that this M also has just a vortex polarities associated to this norm. And further away from the vortices, the vector field M must be locally Holder continuous, where the Holder index depends on this P. And then in our result, we obtained a slight generalization of this Bochard-Pegon result. So this is what we show. We take a bounded open set in R2, and we have a strictly convex C1 norm. Then we show that the zero energy states of the generalized Eikonal equation associated with this norm must have only vortex singularities associated to this norm, and further away from the vortex singularities, this M must be continuous. So this is a slight generalization of the Bochard-Pegon result in the sense that here we are assuming a little bit less, so we just require the norm to be strictly convex instead of the additional power type P assumption. And moreover, here we offer a somewhat more direct proof for this regularity result. In the work of Bochard and Pegon, they essentially adapted the argument by Xavier, Otto, and Pegon in the classical case in this generalized setting. So here we realized that through transformation, we can actually reduce the problem to one in the classical case rather quickly. So specifically, we introduced this mapping n sub gamma. So this is the outer unit normal mapping on this curve capital gamma. So for each point on the curve capital gamma, you map the point to the outer unit normal in the Euclidean sense. So then this is a F1 valued mapping. And then we introduce the vector field M tilde, which is the image of this M under this outer unit normal mapping. So then through some relatively, through some elementary geometric argument, we can actually translate the kinetic equation satisfied by this M to a kinetic equation satisfied by this M tilde. And then it turns out that the kinetic equation satisfied by this M tilde is one that describes zero energy states of the classical Eikonal equation. So it turns out that M tilde is indeed a zero energy state of the classical Eikonal equation. So that we can just borrow the classical result by jumping out into them to get the regularity for this M tilde. And then because the norm is a strictly convex C1, this mapping N sub gamma is a homeomorphism in general. And then the regularity of M is obtained by the inverse mapping of this N gamma, and then the regularity for this M tilde. So this is the how we got to this regularity. And by the way, in the case that this norm is of power type P, as in the work of Bochard and Pegon, we recover their regularity result. And then
so you need the Lipschitz map and to be Lipschitz.
It doesn't have to be, because here we just in general we just can only expect this M to be continuous, not higher. So in the work of Jabinot and Perthan, well, I mean, for this vector field M tilde away from the vortices, it is locally Lipschitz. But when we transform back in the generalized setting, you generally have high regularity because our curve is less regular.
So it's enough to have a homeomorphism.
Right, preserve.
Right.
Just a continuity. So this this M away from the vortices in general is just a continuous. Yeah. And so under the additional, well, if you have more regularity for this C1 curve, then this N gamma has higher regularity. So, well, I mean, this M tilde always have the best possible regularity. And then depending on the regularity of this N gamma, and then you can get higher regularity for this M, just as you wish. Okay, so then for the remainder of the time, I will focus on discussing finite entropy solutions for the generalized Eikonal equation. Let me just recall quickly what we mean by finite entropy solutions. So for the Eikonal equation or generalized Eikonal equation, finite entropy solutions are solutions so that all entropy productions are finite rhythm makers. So in the classical case, it was proved by Guanying and Lamy that finite entropy solutions for the classical Eikonal equation can be characterized by this fractional best of regularity with an index 1/3. This same fractional best of regularity can also be used to characterize a large class of to characterize finite entropy solutions for a large class of scalar conservation laws. So this was essentially done by Guanying and Pegon in 2013. So they considered the scalar conservation laws in one space dimension with a flux function under the assumption that F is uniformly convex. So they obtained the same regularity, so the index 1/3 for finite entropy solutions. So essentially they established the forward implication, and the backwards implication is a simple consequence of a work by Eikonal and Ignat in 2015. And then they also considered more general flux functions satisfying this type of quantitative control. So namely f prime of b minus f prime of w greater than or equal to some constant times b minus w to the power p for all v greater than w. So here this this power p is greater than or equal to 1. In the case where this p, then they established this type of fractional vector regularity for finite entropy solutions. So by the way, this is an optimal regularity in the sense that there exist finite entropy solutions that do not enjoy better regularity. So this was observed by Eikonal and Westickenberg back in 2003. So in the case when p equals 1, so these functions are strictly convex. So this regularity is exactly the one with the index 3. However, for p strictly greater than 1, such functions may have degenerate convexity, as demonstrated in this example. So here we have f of p equal to f value p to the power p plus 1. For p strictly greater than 1, so this function has degenerate convexity at v equal to 0. And for such functions, the regularity is the one with the index P+2 strictly greater than 3. And for such regularity with the index strictly greater than 3, it is weaker than this P1/3 3 infinity. And in general, it is known that there is no reverse implication. And this leaves the natural question to characterize finite entropy solutions for such scalar conservation laws where the flux function may have degenerate convexity. So motivated by this question and also the work by Robin and Lamy in the classical case, we obtained a characterization for finite entropy solutions for a class of generalized Eikonal equations associated with norms that may have degenerate convexity. And this result also sheds light on scalar conservation laws. To explain the result, let me first make some definitions. So first, let's recall that we're using gamma of theta to denote an arc length representation for the unit circle of this norm, capital gamma. And then we choose this function alpha to satisfy this equation. So it gives you the face of this unit tangent vector on the curve capital gamma. So it's uniquely defined up to an additive constant. And then let's introduce this quantity pi acting on gamma of theta 1, gamma of theta 2, so 2 points on the unit circle of this norm to be this double integral. So for both variables, it's integrating between theta 1 and theta 2. And then we're integrating alpha of t minus alpha of i's in absolute value in TPI's, where alpha is this phase function. So this quantity pi can be viewed as a metric to count the jump between these two values, gamma of theta 1 and gamma of theta 2, living on the unit circle of the norm. And this metric has the advantage that it takes into account the fact that the convexity of the norm may degenerate differently in different directions. To just give a little bit more explanation, so here I drew two pictures. So in these two pictures, the gamma of theta 1, gamma of theta 2 are meant to be the same vectors. And they both live on this unit circle of the norm, so this capital gamma. In the first picture, this portion of gamma connecting the 2 points is relatively flat. And in the second picture, this is more convex. And essentially, this quantity pi is somehow just counting, the change in the phase of the unit tangent vector field along the curve gamma. And then in the first picture, apparently the jump along the curve is going to be small, and in the second picture, it's going to be bigger, just because we have different convexity or curvature for the curve. So then with the help of this metric pi, we can achieve the following equivalent characterization for finite entropy solutions for a class of norms. So here we take a bounded open set in R2 and then a strictly convex C1 norm. And then we take a solution of the generalized Eikonal equation associated with this norm. But here we need an additional technical assumption that the alpha forms a doubling measure. So the alpha is this this function capturing the phase for the tangent vector on the gamma. And then with this additional technical assumption, then we are able to show that the finite entropy solutions are characterized by this condition, quantity being finite. Well, this condition here is a little bit technical, and let me try to explain this a little bit. So essentially, if I replace this metric pi acting on m of x plus h and m of x by the pure difference between m of x plus h minus m of x. So if this quantity is finite, then it implies that this vector field m locally satisfies this fractional best of regularity with index p. So for p strictly greater than 3, we know that regularity is not enough to imply finite entropy solutions. So essentially, for this fractional best of norm, it just takes into account the pure jump of the vector field. So then in these two pictures, if you just count, gamma of theta 1 minus gamma of theta 2, then in these two pictures, they're the same. So the fractional best of norm cannot tell this difference. But this metric pi can take into account the geometry and does the job. So in this sense, this is a better metric for our setting. And then with the help of this metric, we are able to achieve this equivalent characterization. And further, a similar condition can be used to characterize finite entropy solutions for a class of scalar conservation laws where the flux function may have degenerate convexity. And finally, for this technical assumption, so even if we assume the alpha forms a doubling measure, we still allow the norm to have degenerate convexity. It's just that the degeneracy cannot be too bad, so it has to satisfy relatively mild quantitative control. Whether this condition can be removed is still not clear to us, but we have done some calculations under the additional assumption that this M is in the BB space. And those calculations under the additional BB assumption, the entropy productions can be computed explicitly using the chain rule. And we showed that entropy productions can be controlled by this quantity even without the doubling measure assumption. So this is an indication that this doubling measure assumption may not be necessary. Okay, so then for the final several minutes, I'm gonna try to explain a little bit the proof of this result. So for the forward implication, it follows rather closely the roadmap that was laid out by Lorent and Lamy for the classical Eikonal equation. So we did some technical adaptations. So the reverse implication, assuming this condition, and to imply that all entropy productions are finite random measures, this is the place where we had to do something quite differently. So let me try to explain this a little bit. We have this assumption, and we want to show that all entropy productions are finite random measures. And then here, the starting point is very standard. So we take a regularization for the vector field M, and then calculate the entropy productions for the regularized function, and then pass to the limit. So it's all standard, similar to what has been done for the classical Eikonal equation. And then after performing this kind of estimates, this leads to the following estimate. So the entropy production of the limit of the vector field M acting against the test function is bounded by some constant times the L infinity norm of theta multiplied by the lim of this integral. So then it just remains to show that this lim inf is a finite number. So in the classical case where this norm is the Euclidean norm, so this integral involving this product that can be estimated using an elegant commutator estimate that was first used by Constantine E and Titi for the Euler's equation, and it was later adapted to this setting by Delitus and Ignat. So in our case, with this more general norm and a different condition, so we had to do something differently, and we had to take full advantage of convexity. By the way, convexity is not used in the commutator type of
So that constant that is there, is it in relation with the curvature of gamma? Because in general, it's right when you write the phi as a tensor M, that psi M, and then we take the gradient of that psi. So that's like the unit there that you see.
So yeah, it's probably there. So the way we did this calculation was again we cook up this transformation to sort of morally speaking transform the unit circle of this norm to S1, and then we did the calculations for unit vector field in S1 valued vector fields satisfying.
Right, but that's the conformal.
So
the conformal factor of your.
Yeah, so that would come into play when we do the calculations. Yes. Yeah, so this constant should depend on the norm.
Why does it have coverage on it? It's only C1, so you don't have
I guess
coverage.
it's convex.
Modulus of convexity.
Yeah, but
Okay, so then let's see. So here for now we want to estimate this product type integral. So for the gradient term, we just borrow the estimate for the class in the classical case. So this is the standard estimate in this business. So the second term, this is something we did differently. So here we write this one as m of x of this norm. So m satisfies the generalized Eikonal equation. So this general norm equals 1. And then here we estimate this difference using convexity. So essentially this estimate is the fact that if you have a convex function, then it stays above any tangent plane. And then we introduce this auxiliary function g sub theta of r. So this is the double integral of alpha p minus alpha of x in absolute value over such symmetric interval centered at theta with radius r. Well, this quantity g is very closely related to the metric pi that we introduced. So essentially, they're both of the form of a double integral of this change of phase. So then it's not surprising that this quantity g can be controlled by pi for appropriate theta and r. However, at various places in our estimates, we had to control this quantity g over larger interval by the quantity pi over a smaller interval. So that is where we need this doubling measure assumption on this the alpha. Okay, so then it's rather straightforward estimate to show that this red term can be actually bounded above by the average of the integral of its g sub theta prime. So here, this inside little g of xc, this denotes the geodesic distance between m of x and m of c along the curve capital gamma. And this theta of x is something satisfying this equation, m of x equal to gamma of theta of x. Now we can put together an estimate for the gradient term and this 1 minus form squared term. And here we wrote the estimate of the first term as an integral of dy, and the estimate for the second term as an integral of dz intentionally, because then when we multiply them, we end up with a double integral on the right hand side. So this is essentially this estimate. So here I use the color blue to keep track of the estimate on the gradient term, and red to keep track of the estimate for this 1 minus 1 squared term. And then this is another place where we make use of convexity. So we introduce the Legendre transform, capital H of theta, as the Legendre transform for this function g. So this is the definition. And by definition, for every pair p and r, the product is less than or equal to h theta p plus r. And then so we think of this as our p, this as our r. So this product is less than or equal to h theta p plus g theta r. And then for both terms, the integration with respect to the other term and then taking the average becomes 1. So that disappears. Now it remains to estimate these two terms. So for the second one, recall that with the help of the doubling measure assumption, so this quantity can be controlled by this quantity pi. So after integrating over omega prime and clearing up this integration with respect to y, which is not hard, so we can show that this can be controlled by this one. And for the first term, it has an explicit form of a Legendre transform applied to the derivative of the function. So then using some explicit calculations based on this fact and the definition of the Legendre transform, we can also manage to show that this can be controlled by pi with the help of the doubling measure assumption. And then just doing a similar game, so integrate over omega prime and clear out the integration of c, and then we can control the integration of this part over omega prime by this quantity. So then at the end of the day, we can show that the integral of this quantity over omega prime is controlled by this quantity, and that shows that this limit inf remains bounded. So that is essentially the skeleton for this proof. I think that's all I want to discuss. Thank you very much for your attention.